Hi, I'm John Pavan. I'm currently a team lead at Bloomberg. This is Lukas Zhao. As you may have noticed from the previous title slide, we are short one person, Aram Chung, who helped develop this talk, and in previous iterations did the first third of the presentation. Unfortunately, she wasn't able to make it to this conference, and so I'll be doing the initial part as well. Since every other talk that I've been to so far at this conference has had a short introduction to the speakers, I figure I should introduce myself as well. So I'm a former experimental nuclear physicist. I've probably been doing software development more or less as the main thing since about 1998, which started off with a book called Computational Methods for Nuclear Physics, which was great because it was basically the Rosetta Stone. It had English description, math description, and Fortran. So that's how I learned. Anyway, I've been doing C++ since, I don't know, 13-ish years ago. Maybe more than that, 15. And anyway, today we'd like to talk to you about how you should design your APIs in order to improve testability for you, the implementer of the library, and for the people who are using your library so that they can use your library in test drivers. Hopefully this will make everyone's lives better. The talk will begin by going through some basic background information about testing. This is mostly to make sure that we're all using the same vocabulary. I know that terms like integration tests and unit tests and system tests are used somewhat differently depending on the group or the company. This is also going to be where the obligatory testing pyramid slide is. It's a testing talk. Then we're going to talk about the motivation for this and review the synergy between the solid design principles and those goals. Then I'll talk about a couple practical recommendations or techniques that you can use in order to apply the solid design principles for testing purposes. And then I'll hand it off to Lukas to further generalize those techniques and some more realistic methods of applying it. So as promised, we'll begin with background and basics. Since everyone's actually at this talk and it had the word testing in, I probably don't need to explain the importance of testing. But I would like to emphasize that testing should be used to verify both the happy path behaviors, how your code executes in the environment that you expected it to execute in, verify that it does what it's supposed to do, and then also how it responds when you're in a situation that's different from that. How does it respond to an I/O error? How does it respond when there's a problem with the database connection? How does it respond when there's something that's a little bit unusual going on? These are typically called the unhappy path behaviors. It's also important to use automated tests. And the basic reason why is that as you add tests, the automated tests can be easily run basically for every change. And as you do so, they continue to protect you against regressions, and every additional test adds value. It adds additional layers of protection. While if you are relying more on manual tests, not only does it take more time to execute these as you add more of them, but also people become numb to things that they have to run manually over and over again, and will actually start to ignore errors that they see. So we want to focus on things that allow people to do automated testing. Also, the different types of testing, unit, integration, and system tests, have fundamentally different roles and provide different benefits, and therefore a good testing strategy should rely on all of them. So here's the obligatory testing pyramid slide. At the base level, you have unit tests, which are tests that basically have your components and your classes in isolation with all of the dependencies stubbed out. There should be large numbers of these. They should execute very quickly. Above that, you have a layer of integration tests. These are your code running in kind of an idealized scenario. So this could be your library being called from a variety of expected use cases, or it could be an actual executable running in a contrived environment. And in these cases, the low-level things like system I/O, system calls, shouldn't be stubbed out, but instead you may have stubbed out versions of your databases or other services that your systems rely on. And at the top, and there should still be a decent number of these, and they can verify both the happy path behaviors and also the error handling and behavior of the system, of your code, for failures of those other systems or reported errors from those other systems. And at the top level, you want to have system tests, which should be relatively few in number, basically because they're hard to set up and deploy, and can be very time-consuming to run, where system tests are your code running in a production-like environment, hopefully still a test environment, but a production-like environment. I'm going into a little bit more detail on each of these, each type of tests. Unit tests, again, are things tested in isolation with everything stubbed out. This includes system calls. It includes everything you can possibly stub out. And because those things are stubbed out, it's fairly straightforward to induce failures that would otherwise be hard to produce in a real environment. So for example, if you have something that relies on a TCP connection and you want to make sure the error handling is correct, then if the TCP connection is stubbed out, you're able to test each of the different ways the TCP can fail in a predictable way and in a timely way. Of course, you should also test that it works correctly when things are working correctly. But the unit tests are really where the low-level error handling can be dealt with. Integration tests, as previously mentioned, basically are your component, whether that's a library or an executable, running in a contrived environment where the things that it depends on at that level can be stubbed out. There's still room here for testing on happy path stuff, but you really have trouble testing the low-level error handling. And instead, the level of unhappy path testing that you have should be things like the service that you're getting information from returns I couldn't find that user. How does your system respond? So this is kind of a higher level of test. These are still very important, should be executed every time, even if they take hours to run. And then the highest level tests are system tests, which we won't really focus on during this talk, basically because we're concerned with how do you design APIs, and system tests are things deployed to a production-like environment, and therefore not directly subject to what we're discussing. But system tests more or less handle happy path behaviors because it's difficult to induce interesting errors if you're running in a production-like environment. So revisiting our testing pyramid slide, we're focusing on integration and unit tests. That's mostly where the advice that we have for you today is going to be applicable. So going to our motivation from the API design talk last year, and I didn't remember to turn off my phone this year. One of the goals that we have for API design is that we want to design for testability. That is, how does the implementer of the library test the code, test the implementation. You get a big help from this by following the solid design principles. And you also want to design your APIs so that the people who are using your libraries are also able to write their own unit and integration tests. There are a bunch of different ways that you can do this. We'll cover at least a couple of them. But if you do decide to do this via mocking, then the library implementer really should be providing the mock objects to make it as easy as possible for the people who are using the library to actually write their tests. It also gives you a bit more control as the library implementer. We'll now quickly review the solid design principles. In case you don't remember them, the single responsibility principle, the open-close principle, the list-scuff substitution principle, the interface segregation principle, and the dependency inversion principles. The single responsibility principle is exactly what it says on the tin. Each class should basically do one thing. This basically means that you should, if you have one class that does a bunch of different things, probably done something wrong. It's better to have multiple classes, each of which that do a set of things that are at least coherent. Pairing the single responsibility principle with the interface segregation principle helps a lot with testing and overall API design, but specifically for the context of this talk, means that you really want to avoid test-specific APIs or functions on your class implementation, on your public API. Well, that's a big limitation. We'll discuss at least two methods of enhancing your test APIs for testing purposes only. Next, we have the open-close principle. Software entities should be open for extension but closed for modification. If something's open for extension, that means that you should be able to add new functionality without modifying existing code. In the context of this talk, we're primarily interested in the modern polymorphic version of this, which is that you should basically have an abstract interface and the multiple implementations. This is generally quite helpful, especially if you have to have multiple different implementations, because say you have a Linux implementation, a Solaris implementation, a Windows implementation, and a Mac implementation. But it also helps a lot with testing, because you can have a test-specific version of that API, and you can provide this for someone who is using your library if you're looking for the library design. Of course, this not only helps you because of the Liskov substitution principle, which is also known as strong behavioral subtyping. And this basically states that you should be able to replace a class with any class derived from it without breaking what's using it. So if you have a class that's using an API, using an interface, then it shouldn't matter to that class whether or not it's using the production implementation or a test implementation, and therefore the test implementation can be used to verify the code that's using it. The interface segregation principle states that no code should be forced to depend on a method that it doesn't use. This is extremely closely related to the first one, which basically means that you should split interfaces into smaller ones in order to avoid making people implement things that they don't actually use. Sometimes when you do that, people will add functionality that you do not expect, and that can cause weird bugs many years down the line, as I was dealing with last week. The final one is the dependency inversion principle. This is basically that high-level modules should not import anything from low-level modules, and both should depend on abstractions. Or abstractions should not depend on the concrete implementations. The concrete implementations depend on abstractions. This basically means that if you're using code, you should be calling an interface, and if you're implementing code, you should be inheriting from that interface. This is extremely common, as we have reviewed the same slides, and they basically all point to the same thing. Have an interface there, an abstract implementation, and then you can add your test class fairly easily. We will review how each of these applies to the different techniques that we suggest momentarily. But as we move out of this section, we have a couple of additional things to emphasize and to include in the list of things that we're considering. The first of these is that the APIs really shouldn't have any features that exist only for testing, or the public API shouldn't have any things that exist only for testing. That just makes things difficult, easy to misuse, more than easy to use. The API choices that you make also should not prevent testing. Some of the techniques that we're going to recommend actually have implications on how other classes need to design their APIs. Of course, API design is an art, so I'll point it out, but be aware of that implication. That may or may not give you pause in taking our suggestions. And that you're going to need a way to stub out system dependencies. This can be anything from the file system to I/O to whatever else you're relying on from the underlying operating system. So I'll now move on to a couple techniques. The first of these is the pointer to implementation idiom, which is primarily useful for helping the library implementer test their code. The second one is that you should depend only on interfaces, as mentioned several times during the review of the solid design principles. And there are a couple different techniques that you can use for this, or things that are extremely similar to it that may or may not be applicable to you depending on what the particular constraints of your environment are. I'll then go through the first of the ways that you can add test-specific APIs without having them in your public API by basically describing something similar to a resource acquisition as initialization guard before reviewing the abstract factory method and both how that can be used to make it easy to switch between your production and test components, and also how those test components can actually be extended by the abstract factory implementation itself. So if you're unfamiliar with the pointer to implementation idiom, sometimes called PIMPLE, it basically states that the implementation detail should be stored in a separate class from the public API. This allows you to have a bunch of different implementations depending on the system that you have. You can have a different implementation for the test. You can have a different implementation depending on the hardware environment. You can have a different implementation depending on the operating system that you're in, whether or not someone has paid for a particular license. There are a whole bunch of reasons why you might have different implementations. And it's quite handy because you only have to worry about the specific version of the implementation that you have when you are instantiating that object. The way that this helps you when you are actually building your library and testing your library is that since you have each of these implementations as their own things, independent from the public API, you can call each of them directly without having to worry about the appropriate setup. Of course, if it's a hardware or operating system limitation, you probably still need to be on the right operating system or hardware. But it does mean that if you have things that vary for other reasons, you might be able to call them all from one environment. And kind of an added benefit is that if you do have anything that is specific to, or that you need to test anything that's specific to the internals of one of those implementations, you can have direct access to that rather than having to go through a somewhat odd pattern to get at it from the public API. So on the left, we have the class foo implemented without the pointer to implementation idiom. That's going to have some number of member variables and types and things like that above the public function, or the private stuff. It'll have some amount of public interface. And if you need to test any of this stuff, particularly anything that depends on any environment variables or any of the other things that we previously discussed, you're going to have to actually set all of those up. And this makes it much harder to write your tests. And it also gives you less trust that you're actually executing the part of the code that you think that you're executing, which you may be able to convince yourself that you're doing it right, but every time someone new comes to the team or you invite someone else to look at your code, they're going to question it. So instead, if you have the structure on the right, where you have a foo implementation that has some amount of internal structure, it has its functions, and then the class foo, which holds a foo implementation and then just calls the implementations, versions of the same functions, you can test all those foo implementations directly. So I'm going to be citing examples from Bloomberg's open source libraries. In particular, I'm going to be bringing them out from BlazinMQ and BDE. BlazinMQ we open sourced in 2022. It is a message queue system. The core of it is written in C++. It also has Python and Java clients, as well as C++ clients. And it's really good if you require fan-out type functionality. So consider it if you need fan-out functionality from your message queues, or you can do out of order stuff. And the other one is BDE, which is our open source our standard library implementation, a whole bunch of utility classes, and kind of a bunch of convenience stuff. So anyways, this one's from BlazinMQ. The CRC32 checksum has a public API called calculate, takes some data, and does a CRC32 calculation. But if you actually look at the underlying implementation, there are two versions of this. One of them uses the CPU, calculate software, and the other one relies on hardware acceleration, which is calculate hardware serial. If you did not have these as the pointer to implementation versions, you would have to set up both of these basically on different systems, because if you're talking about a hardware limitation, you'd either have the hardware or you wouldn't have the hardware. But since we have the pointer to implementation version, if we have one that has the hardware acceleration on it, we can just call both of them on that and we'll be fine. Makes it a little bit easier. So now let's go back to the idea of depending only on interfaces, which helps both the person implementing the library and the people using it. So these recall the polymorphic open-close principle, discuss substitution and dependency inversion principles. It makes it significantly easier to implement mocks and stubs. And as a reminder, you might need to stub out anything, or you should stub out anything that you might need in order to write tests, and this includes system calls. We'll offer a specific recommendation there momentarily. So if you're dependent on interfaces for how things are actually being executed, then you're going to end up having to deal with a little bit of lifetime issue stuff, because your constructor is going to end up needing to take pointers to those interfaces or reference to those interfaces or whatever your chosen mechanism is, store those for future use, and then when the functions are called, they can use that underlying information. But of course, if you need to rely on something that doesn't provide an interface by itself, say a system call, then we suggest that you might want to consider a functor. This gives you the ability to stub out something like open file, which would normally return an integer in order to do that, be your file handle, with something that you could say failed to open file in a predictable way, rather than trying to set up those conditions at the operating system, or actually on the operating system level, or failing to open a TCP connection or something like that. So then you can put in test functors in order to mimic the behavior that you want specifically for your testing. But of course, if you wanted to keep your API easy to use and difficult to misuse, the default behavior needs to be the production behavior. So you need to remember to include that. So that's why the default version of the functor should be the production behavior. Of course, you want to make it as easy as possible for people that are using your library. So you should provide an interface for the classes that you implement. So basically, if you have foo, you should have a foo interface and inherit from foo. This requires some additional typing. As Lukas will mention, we may be able to provide some help with that in the future. Of course, you may be in an environment where you can't really use heap allocations, and therefore things like the polymorphic inheritance don't work out all that well for you. And in this case, you can do something extremely similar by using templates. I think Dewhurst wrote a paper on this a while back. But basically, if you have a class that has a dependency on some type named bar, then it can take a pointer or reference to bar, store bar for future use, and then your real foo, your real implementation of foo, is just a foo that depends on a real bar, and your test foo is a foo that depends on a test bar. Of course, if you're doing this and the situation allows, again, I don't know exactly what your constraints are. If you're in an embedded system, maybe this is a terrible idea, or a safety critical application, then the foo interface, you may want, anyway, if you can, then please provide a foo interface so that people who are coming after you don't have to repeat the same thing with the template. It is a little bit more difficult to use and a little bit more painful. The example that I like to cite here is coming from BDE, and while it's not strictly an interface, it does have a couple concrete functions. Basically, the BSLMA allocator gets used all over the place in BDE. And there are a couple of versions of it that are extremely handy. For example, the test allocator is very, very good at finding memory leaks in test code and unit tests. And the local sequential allocator can provide really meaningful performance boosts under the right circumstances. So now we'll move on to something that I find a little bit more exciting, and that is how to add test APIs using something that resembles a resource acquisition as initialization guard. This is really handy because, as previously mentioned, the single responsibility and interface segregation principles really put together mean that we want to avoid test-specific functions and methods in our public API. So a good example of this also comes from BDE, which is coming from the event scheduler implementation. There's also an event scheduler test time source. So the event scheduler is just a class that you can schedule functions to happen at specific times. So you can say, hey, event scheduler, here's a lambda. I want you to invoke it in a minute. Hey, event scheduler, here's a lambda. I want you to invoke it every 30 seconds. You can do different things with it like that. Of course, if you're trying to use an event scheduler and to test things that are built using an event scheduler, particularly in your unit tests, you don't want to actually wait 30 seconds or wait a minute to see whether or not something happens. Instead, you want to have a mechanism for advancing time relative to that event scheduler so that you can see what it actually does and how your system behaves under those circumstances. So to this end, you can, after you've created your event scheduler, you can create an event scheduler test time source, which takes that scheduler as an argument. Then you are free to start the scheduler, do whatever it is that you're going to do with that event scheduler. And then when you want to see how it behaves as if some amount of time had passed, you can call advance time on the test time source with some time interval, and then the event scheduler will behave as if that amount of time had passed. Makes it much, much easier to write unit tests. Things are way more predictable. You don't have to worry about your tests running for hours because you have all these 1-minute delays. Just makes life a lot easier. And you don't have to manipulate artificially low delays and things like that in your code, only for testing purposes. So let's now look at how you might go about adding this, or how you might go about implementing this in a fairly, very simplified way. Basically, if you have your class foo, and there's something underlying that foo depends on, then you're probably going to have a functor or a data class or an underlying implementation that is being held by foo. You'll also need to friend the test guard, and then foo would just have its normal constructor and the normal public API. Then your test guard would take foo as its argument. It would modify the thing that foo is actually depending on for functionality, and then the test guard would have those public APIs, or have the test-specific APIs that would allow foo to be more easily tested. So the question was, since we have to modify foo anyway in order to add the test guard, why not just have foo fully own the test time source?
Yeah, like in the examples you showed.
Yeah. I think I'm going to get to that literally on the next slide. But the underlying thing is that this is kind of the early. Yeah, let me go to the next slide, and you can tell me if I actually answer your question. There is an underlying implementation, or underlying problem here, and that is if you have a class that fully owns a foo, you don't have any way to install the test guard. So there's no way to add the underlying implementation, or the test implementation there. So instead, you have to have. I'm now realizing I'm not actually answering your question. So I'll finish this slide anyway. So instead, this is a usability implication for the people using your class, and that is that if you end up having to have a class that uses a foo and takes it as an argument, so that the test guard can be applied before the foo comes in, because if it is wholly owned by the class that's using it, if it owns foo as opposed to uses foo, there's no way to extend to that API. Okay, so going back one slide. So yes, you do have to modify foo in order to allow this, but the fact that the foo test guard is a friend is not part of the public API. So that's still hidden from your end users. And it's still, and even if it wasn't, it is still logically isolated. The test guard is still logically isolated from the foo implementation, which makes them much less likely to accidentally try and use the test API as part of their actual code, or basically by accident or through intentional misuse. So a logical separation. Yes, sir.
But if you make a class,
So the question was, if you do have this test guard, which isolates the test API separate from foo, then you end up being tempted to add a significant amount of test APIs on the test guard, rather than having a limited number of them on foo. So API design is an art. There isn't one unique choice. This is more or less trying to, so the problem with having any test APIs on your public interfaces is that people can accidentally use them in their production code. So this means that it fails on the easy to misuse. A good API is supposed to be hard to misuse. And if you have public test APIs, or if you have test APIs in your public interface, then it's very easy for people to call those. And this can be a problem either because they're calling them accidentally and therefore they're inducing test behaviors in production code, or because they have gotten really clever and they're intentionally doing something that you never designed your class to respond to, at least not in a production way. And then they may call you out and give you bug reports saying, hey, after I call this thing, this other thing stops working. So this is the kind of the same reason that you don't want to return a reference, especially even a const reference from a public API if you have anything that relies on what happens when that variable is updated. Because even if you return a const reference, someone can strip away that const with the const cast, modify that variable directly, and then if you had, say, a threshold being checked with that variable changing, and they say, hey, the variable being checked no longer works, and you actually get their code, you see that they're modifying the value directly independently from the API that you provided. Well, that's really annoying for you, but also you're the one that provided that API. So you want to really lock down, you want to carefully consider what public users of your API can do. So this is largely for logical reasons rather than the convenience reasons. This is meaningfully more work for the library implementer in the short term, but it ends up being much less work for the library implementer and is logically much easier to use, conceptually much easier to use for the people that are using the library. You're free to disagree with me on that. So, okay. So the last thing I'd like to discuss before handing it off to Lukas is using the abstract factory pattern. The abstract factory pattern just means that you have some sort of factory interface, and the purpose of this factory interface is to provide the concrete types for for the use in the rest of the library or the use of the rest of the application. This is extremely handy for swapping everything over in exactly one place because that means that the only time that what these types are, that choice is made only when you provide the concrete implementation of the factory. And so that makes life much easier in a bunch of different ways. And if you want to do it just for convenience sake, this also helps if you have to pass a bunch of things into a constructor. But that's probably not the right use case. So the Gang of Four book uses this, switching between motif and other UI widgets. I'm just about old enough to remember motif. And I hope that whatever software they were using has at least been updated to use less teeth, which is also totally obsolete. And I saw one person smile. So from a testing perspective, this basically lets you easily switch from the real versions of your widgets, the real versions of your classes, and whatever underlying implementations you rely on, or the ones that you're providing to a library user, to test versions in a single place. So this can make things much simpler for you. But as cited in this example, also from BlazinMQ, it can also give you a nice place to add test-specific functionality. So if you have a channel factory, which in this case has a function called listen, which populates a handle. The handle can then be later used for I/O. The test version of this factory not only has listen, but it also adds a reset method, direct methods for setting the listen and connection status, access to all of the properties for the connection, direct access to all the listen calls, the connect calls, and the cancel calls. So this is another way that you can add functionality, as well as making your life much easier by making it much easier to manage both your dependencies and the things that you provide. So I'd now like to hand it off to Lukas in order to further generalize and make some somewhat better recommendations than I can.
Thanks, Zhao. My name is Lukas Zhao. I'm also a former physicist. Now I'm a senior software engineer at Bloomberg. So now we're going to discuss some general techniques of mocking and testing. And we're going to discuss some challenges that we may face using these techniques. And in the end, we will propose a new tool that aims to solve these challenges and make life better. So as we discussed earlier, mocking with dependency injection can be done using an abstract interface or using a template type. And also we're going to discuss who is responsible for dependency injection. So here is an example. This is a generic example of using an abstract interface here. So we have a pure virtual interface class dog I here, and it has a pure virtual function bark, right? So this interface is the abstraction that other component can depend on, right? Following the principle of depending on abstraction, not the concrete implementation. The concrete implementation of class dog is also derived from the interface dog I, and it overrides the bark function with a real implementation, and it defines what it actually does in production code. We also have a dog mock here, and the mock class is also derived from the interface class dog I, and it overrides the bark function with a mock function here. And in this example, the mock function is implemented using Google Mock, right? So when another component here, my business, wants to depend on dog, what it can do is it holds a pointer pointing to the interface type dog I, right? Then its constructor opens up for dependency injection here, and in its business logic do something here, it will invoke the bark function through the interface type pointer. So in the production code case, right, we would inject a real dog when we construct my business, right? Then the real function bark would get invoked in do something function. But when I do my unit test, I would inject the mock, dog mock in here, and the mock function would get called in my test. So the tests usually look like this, right? So in the testing fixture, I can declare all my mocks first. Then I will declare my subject under test SUT. Then in the setup part, I will instantiate all my mocks first. Then I will instantiate my SUT. And here's where I inject all my mocks dependency into the SUT. So when I actually test my business logic here, we're saying here when the business do something function gets called, right? We can expect our mock function gets called in a certain way. So mock function is very flexible, and we have full control over here. We can verify how many times the mock gets called, what arguments, what values are sent to the passed to the mock function, And the mock function, we can also tell it what to do on the fly. For example, returning a certain value, or if some arguments are of pointer or reference type, I can even tell the mock to set the storage value to those arguments, right? So they're very flexible, and we have full control in our tests. Now here's an example of using template type for dependency injection and mocking. And as we stated earlier, we generally don't recommend this approach unless that your code does not allow dynamic memory allocation, or that saving one CPU cycle is really a gain. Okay, so next we're going to ask the question, who is responsible for dependency injection? So here we have a awesome lib class here, just like we talked earlier. It's properly written, it derives from the interface awesome lib I, right? And its constructor opens up for dependency injection with the A service interface, B service interface, C service interface here. So that looks fine. But if you give this to the user, right, at some point, your user will be faced with the burden that they need to inject the real APC service when they construct your awesome lib. So this is something we don't want to burden our user with. For one thing, right, why do they care? And also, these are the implementation details of our library. We should not expose them to our user. So what can we do here? One way to solve this problem, again, come back to the pimple idiom introduced earlier. So in this case, we have our interface, we have our mock, and we have our awesome lib. But you look at how the awesome lib is implemented, right? So the awesome lib holds a pointer pointing to another type awesome lib imp here, right? So the awesome lib imp actually opens up for dependency injection with the interface of A, B, C services here. Then what the awesome lib does is, in its constructor, it will actually construct all the real dependencies and do the dependency injection, inject them into the awesome lib imp, right, with the real ABC service. And then it will forward all the calls to its member function to the awesome lib imp. So this way, we can ship our library with the interface, with the mock, with the implementation to our user, and our user is not responsible for injecting any dependency that they don't care about, right? And in the meantime, we can fully, properly test our own business logic by unit testing the awesome lib imp, where it opens up for dependency injection and where we can inject the mock of the services in them in our unit test. All right? So another approach is, oh wait, sorry. So the code of, before I jump into another, the code for the pimple idiom looks something like this. We have our awesome lib. It is derived from the interface awesome lib I. It holds a pointer pointing to the implementation awesome lib imp, right? So you see in this example, in the constructor, it constructs all the real ABC service and does the dependency injection, inject them into the awesome lib imp class. And it also forwards all the calls to its public function talk here, forwarding them to the awesome lib imp talk. So for the awesome lib imp class, it opens up for dependency injection. And here we can properly, fully unit test our business logic by unit testing awesome lib imp, where we will inject the mock into our SUT. Then another technique is called poor man's dependency injection. There are many variations of implementing this. A popular one is this. So basically what it does, it has two overloaded constructor here. One version of a constructor actually instantiate the ABC services with the real service implementation here, right? So this version of constructor does not need user to inject anything that they don't care about. So this version of constructor is probably the one you want to give to the user to call when they use your library. And you have another overloaded constructor here that opens up for dependency injection, and you probably will want to use this one in your test where you inject the mocks into the SUT when you do the testing. Okay, then we want to discuss some challenges using these techniques. So from what we just went through with Zhao, and the example I just had here. So immediately you can see that the upfront investment for the properly testable code is not pleasant. To write properly testable code requires you to write more boilerplate code and with more files, right? So this is something like especially painful for new C++ programmers. And even if you're successfully convinced them that typing the keyboard is never the bottleneck of your software development cycle, it is when the bug that escapes to production come back to bite you, you have to do the debugging and the fixing. That is a pain point, so fine. But then they face the challenge that they don't know a lot of these techniques and patterns and practices, right? So moreover, when usually in our work life, there's a small change requirement coming in, right? It seems so much easier if you just add 3 lines that make it work without thinking about testability, we're thinking about principles, right? Design principles. So these are often the difficulties we face when we teach our new C++ programmers. So we thought about this question a lot, and we think a good solution is to have some tools that to make it easier to do the right things instead of doing the wrong things, and something like a one-click pattern generator, right? So we're proposing a tool here. This tool will ask you some questions, understands what you need, right? And then it will generate all the boilerplate, generate the mocks, the interface, make it easy to do, the dependency injection, the EDMs, the patterns, right? Then in that case, then we remove this burden from the developers and make it easier for them to get on the train with the writing proper code. So this tool does not only make it doing things faster, also doing it better, right? As we mentioned, it encourages you to write small classes right out of the way, right? Because when you have such a tool, you don't really need to just piggyback some lines in the existing class, existing file. You can just run this tool. It will generate for you, right? So you can write more cleaner code. It always generates tests right out of the box. So you can just focus on writing new functions while you already have to immediately start writing tests for it. It creates interface, mocks on demand, create pinpoint EDM to further isolate dependencies if you want to, generates useful hints, and it also sets a good example for modern C++ practice. So we should have some more answer to this in future, so watch out for Bloomberg BB GitHub. So that's it, that's the talk. Thank you, and we will take questions if you have any.
This all works great for synchronous code. How about asynchronous? Any hints? Asynchronous code handling with these approaches.
Sorry, could you repeat that?
Synchronous. You mentioned everything synchronous. Synchronous call. You invoke, you wait, it releases, you get back your something. But how to approach testing asynchronous code?
Okay.
You invoke something, you don't get it back.
Right. So when you strictly talking about unit tests, right, it should not involve, when you're testing original nature, it should not involve threadings, right? So when you write cleaner code, you would put the job, so to speak, right? The one that doesn't involve the thread into one class and one function, and then it will be hooked with another thing like a scheduler or thread pool, right? So you unit test the job where you don't involve with the threads. So does that answer your question?
Can I try?
Yeah.
So all these techniques should be applicable to asynchronous code as well. It's a little bit more difficult to write those tests. But generally speaking, it's very easy to convert asynchronous code to synchronous code. So when possible, you should probably start with the asynchronous code. And again, all of these techniques should work. It's just that writing the tests is a little bit more complex. And you can convert asynchronous code to synchronous code trivially in a unit test. All you need to do is stick a barrier in your callback.
And then again, if you have enough abstraction, if you have enough separation concern, it's usually doable for the separating the job part and the part where you hook up with the multi-threading part. Right?
So I'm just curious. You talked about blazing MQ, and it's right there in the name that this is like it sounds like a very performance-oriented type of messaging queue solution. I wonder if you ever got pushback on the added indirection that you're doing, just for testing, quote unquote. Did anyone consider this trade-off not worth it?
So for blazing MQ, since it is a message queue system, it's going to be, performance impacts are going to be dominated by I/O. Although there are some performance concerns that we are going to be addressing, I think, in the relatively near future. Cameron, do you know what the schedule for that is?
I haven't looked at it.
Okay.
No, but like generally speaking, so maybe in another library or anyway, did you ever get pushback performance-wise because of the added indirections?
Yes, you can get pushback on that. It depends on the type of code that you're doing and whether or not the performance hit of a couple additional lookups actually makes a difference relative to all of the other things that you may have to be waiting on. I think both of us work on relatively complex applications, and therefore the cost of going a few more layers of abstraction is relatively trivial in terms of the amount of work that we have to do. Of course, if you're really interested in performance tuning, then look at the template versions of things that we recommended, because that does get rid of a lot of that overhead.
So yeah, a lot of these techniques, or really, I guess all of them, depend on an extra layer or layers of abstraction. And obviously that makes it a lot more flexible and allows you to do this testing. But approaching this from not a performance perspective, but a code readability and sort of static analysis perspective, how do you balance that testability versus readability and ability to follow the code without stepping through it in a debugger due to these abstractions that have been added just for testing?
So that is an excellent question. So unfortunately, API design is an art, and so you need to balance the various goals against each other, with one of those goals, of course, being things should be easy to use, which includes meaning easy to debug. A few of these techniques, even though they do add a layer of abstraction, do genuinely make things easier to read and easier to understand. So for example, using the pointer to implementation method and isolating a particular version of the implementation from a different version of the implementation so that you don't have to switch between all of the if-defs as you're trying to comprehend it, actually does help quite a lot. But yeah, API design is an art. So these are recommendations, these aren't prescriptions. These might be something that you find useful.
I want to add testability and the good design goes in hand, right? So we were talking about readability. If I have a better abstraction separation concern, my test will look much simpler instead of involving like 3 layers or 4 layers of things instead of just 1 layer with mocks. If my test looks much simpler, right, then must be my API is much easier to read, right? It does this, does this, does this, win this, and win this, right? So, yeah.
As you get, I didn't get satisfied with the asynchronous part, so I wanted to ask it in a different form. You had a slide where you said implementation should not be influenced by the testing. Somewhere it was there. You said something like this. And in my company, we do a lot of low-level parallel concurrency, so you cannot guarantee in a particular class that you're not starting using a thread or some asynchronous code invocation. And what we ended up is to actually have functions. So you have a function, you have input and your output. In your approach, why you're not suggesting doing something like this, where instead of having all these indirect dependencies you're actually mocking for tests, you can traverse it into a function where you have all your inputs and all your outputs are defined in a single place, so that you can actually have even your asynchronous code be tested this way.
So this is the data-driven
Yes.
data-driven design. Okay, so for data-driven design, kind of your data structures would end up, you have two choices. You can either have your data, the data structures holding those layers of abstraction, which may be extremely inconvenient or impractical. Another way to do it would be to pass those in as arguments to the functions that you're calling. Both of those have their own problems. And again, this is an art, it's not a design. You can take these recommendations or they may not be useful to you. I don't know, but I hope they are. But those would be your choices under a data-driven design. You can either have the containers that contain the data, hold the abstraction layers, or have the abstraction layers passed in as arguments to the functions that are calling it. Or you could have the functions that are being invoked on the data layers not be static or globals. Instead, they could be members of a class, and that class could still hold those layers of abstraction. But the data that they act on still be coming from your data classes. There are a bunch of different ways you could do it, but again, we're making suggestions. Hopefully some of it's useful to you.
Have you already started working on this new tool, or if you have, how far along are you accomplishing all these points?
We don't have the permission to talk about it.
But it would be a real nice tool to use.
Yeah, so I think.
So the answer is we will start the process as soon as we get back. What Lukas said.
But when we have an update, it will be GitHub on Bloomberg's GitHub. Well, Bloomberg on GitHub.
Yeah. We're allowed to talk about the implementation at all? And like what use case we would be we're in?
So I think mostly it answers this. Then again, it asks you questions, understand what you want, and give you as much as possible. It will generate things that you can compile right out of the box. You can just focus on implementing new functionality, adding tests. So that's the specification. We cannot talk about if we're implementing how we're going to implement it. Yeah.
So that, as implied by that, it would not be a tool that you could apply to existing code in order to add these abstraction layers in a seamless way. That might be something that someone could implement using several of the Clang libraries, but it's not something that we're working on. Okay, thank you very much, everyone. And I guess we should say Bloomberg is hiring, so if you're interested.